This is a satellite foundational course for GOES-R on multi-channel interpretation approaches for use with the ABI. It includes information on band differences, why they work, and what information they show, and which band differences are in AWIPS, and on RGBs, red, green, blue composites, including the baseline RGB products in AWIPS. The topics of this training are related. There are different ways of looking at channel differences from the GOES-R Advanced Baseline Imager, or ABI. You can look at difference fields, brightness temperature differences for IR, or reflectance differences for visible and near IR. You can toggle between fields, and you can look at RGBs. RGBs are created by assigning an individual band or a band difference to the three color components, red, green, and blue, that are used to create an image. All of the ways of looking at channel differences highlight the sensitivities of the individual channels. This chart lists out the bands that are available on the GOES-R ABI. The chart shows 16 bands, the central wavelength, the wavelength range, the resolution, and the band nickname. The nickname gives you an idea sometimes of what the band can be used for. There are lots of other possibilities, however, that extend beyond the nickname. Band placement is typically related to absorption by a particular gas, be it water vapor, sulfur dioxide, ozone, or carbon dioxide. Bands are also placed in regions where there is little absorption by atmospheric gases. When you are looking at band differences, or RGBs, or even just comparing one band with another, it's important that you understand the physics of the bands in question. Why is that particular band included on GOES-R? When band differences are considered, what differences between the bands exist and why? Some of the bands used in band differences are displayed on this slide and will be considered more in depth in this training. Some brightness temperatures are very well known and used often. Those are listed here. That they are so well known underscores why those channels are included on the ABI. There are difference fields that are created in AWIPS. These are all simple difference fields except for NDVI, and that's defined on the next slide. What is the principal cause of the difference that you see between the two channels? This color-coded slide lists out how differences between the two channels occur, whether that's by differences in absorption, usually absorption by water vapor, emissivity differences, differences in reflectance that occur only during the day, and transmissivity differences. This chart that you may have seen before shows the infrared channels on ABI. The blue regions show where individual bands are detecting energy. Some are narrow, like band 10, and some are relatively wide, like band 8. The red line can be interpreted in two ways. It's either the relative amount of absorption by any gas in the atmosphere, or it's the brightness temperature sensed by the satellite in clear skies. Cooler brightness temperatures result when absorption by a gas occurs in the atmosphere. Strong absorption by water vapor is apparent in bands 8, 9, and 10. Ozone absorption is occurring in band 12. CO2 absorption occurs in band 16. These bands will all show cooler brightness temperatures in clear skies. When the red line is near zero at the bottom of the chart, little absorption is occurring, and the satellite will detect the surface temperature. This is the case for the 10.3 micrometer band 13. Compare that to band 15 that has more water vapor absorption spikes. The split window difference will highlight the moisture distribution in the atmosphere. The split window difference gives information about low-level moisture distributions that might not be observable in the visible imagery. This is an example from 2017, and it ended up in a publication by Dan Lindsay that's available at the link. A challenge with the split window difference, however, is that it is strongly influenced by skin temperature changes. So this one is at 1547 UTC, and here we have the same thing at 1847 UTC. If you compare this split window difference with the one on the previous slide, you'll see big differences in values that aren't related to moisture differences. The enhancement here might not be useful for identifying the gradients associated with the moisture tongue that you saw on the previous slide, but do note how the convection developed right within the moist tongue identified by the split window difference. The split window difference also detects dust. When energy radiates upward from the surface through a dust layer, the amount of absorption and subsequent re-emission varies with wavelength. In particular, dust is a good absorber of 10.3 micrometer radiation, but a not so good absorber of 12 micrometer radiation. So 10.3 micrometer energy leaves the warm surface, absorbed by dust higher in the atmosphere, and then re-emitted from that higher level where the temperature is cooler. 12 micrometer energy leaves the warm surface, passes through the dust layer without being absorbed as much, so there is less re-emission from the colder higher levels. Thus, the 10.3 micrometer brightness temperature will be cooler than the brightness temperature at 12 micrometers because of dust. This is opposite to the effects of water vapor. It's common for dust RGBs to include the split window difference. The dust-water vapor absorptive differences for the 10.3 and 12 micrometer channels are mirrored in the ice absorptive differences at 11.2 and 8.4 micrometers. Why does greater absorption lead to cooler brightness temperature? Much of the 11 micrometer energy upwelling through an ice cloud will be absorbed and then re-emitted from the colder temperature. Proportionally, not as much energy at 8.4 micrometers is absorbed. If there isn't absorption, or if there's less absorption, the emitting surface will be farther down in the atmosphere, closer to the surface, where it's warmer. In this example of convection off the South Carolina coast, thin cirrus, as inferred also perhaps by the inset 1.38 micrometer band 4 imagery from ABI, shows as magenta and white, whereas thicker cirrus is blue. That is because more low-level 8.4 micrometer energy is upwelling through the thin cirrus. 11.2 micrometer energy there is more likely to be absorbed. There are also subpixel effects that must be considered in any brightness temperature difference field. There isn't really a subpixel effect in clear fields of view or in completely cloudy fields of view, but there is a big impact for partially clear fields of view. When a cloud does not completely fill a pixel, parts of the pixel will be filled with colder regions and parts will be filled with warmer regions. Shorter wavelength detectors are more sensitive to these warmer regions, and longer wavelength detectors are more sensitive to colder regions. This subpixel effect leads to differences in computed brightness temperatures in the ABI bands that are independent of gas absorption. The plots on this page document subpixel effects. 4 window channels, bands 11, 13, 14, and 15, are in the upper left. This is from AHI data, so the central wavelengths are 8.6, 10.4, 11.2, and 12.3 micrometers. The detected temperature is cool for this thin cirrus as the wavelength of the observation increases within the purple shaded region. Notice how the bar plot is shifting to colder temperatures as you go from shorter wavelengths to longer wavelengths. Similarly, the scatter plot at the bottom comparing the 8.6 micrometer to the longer wavelengths shows the warmer temperatures for the 8.6 micrometer in this cirrus region. The night fog brightness temperature difference is another well-known field, and it's used to identify regions of low stratus and fog. Clouds made up of water droplets are not black body emitters of all wavelength radiation. Satellite detectors of radiation simply collect a number of photons. The conversion of those radiance counts to brightness temperature assumes black body emission, however. So if a surface hasn't emitted as a black body, meaning fewer photons than a theoretical maximum have been emitted, then the inferred temperature will be cooler. This occurs for 3.9 micrometer radiation above clouds made up of water droplets, but not for radiation around 11 micrometers. So for water-based clouds, the 3.9 micrometer brightness temperature is cooler than the 10.3 micrometer brightness temperature. In this cross-section from a fog bank to a cirrus deck, incidentally, this is one of my favorite figures, You see differences in the brightness temperatures that are related to the emissivity differences in the low stratus, so that the 3.9 micrometer temperature is cooler than the 10.7 micrometer temperature in this case. And you see transmissivity differences in cirrus and subpixel effects, so that the 3.9 micrometer brightness temperatures are warmer than the 10.7 micrometer brightness temperatures. In clear regions in the middle, the two brightness temperatures are similar. It's not only clouds that can affect 3.9 micrometer temperatures. This graph shows emissivity over water, pretty close to 1, dry sand, red clay, and tree leaf. Dry sand and red clay have emissivities that are much less than 1. Blackbody temperatures over this will be cooler than blackbody temperatures computed at other wavelengths where emissivities are closer to 1. Keep this in mind when you're looking at brightness temperature differences that key off emissivity differences. Reflectance differences are what's important for visible and near-infrared channels, as shown in this chart showing the 2 visible and 4 near-infrared channels on ABI. Note how much more reflective grass is in the 8.6 micrometer band 3, so-called veggie band, than in the 0.64 micrometer visible. Note how much more reflective snow and ice are in the visible than in the 1.6 micrometer channel. These differences can be played off one another to highlight features in either difference fields, or in RGBs, or in simple comparisons of 2 bands. In band 3, the veggie band on ABI, 0.86 micrometers, green vegetation is far more reflective than in the visible channel. Thus, this band excels in distinguishing between land and water. Bodies of water surrounded by land will really pop out, so it's great for examining changes due to excessive rainfall, that is, flooding. Because green land is so reflective, though, clouds are sometimes hard to distinguish over land in the 0.86 micrometer. There's more contrast in the visible. Snow and ice clouds are highly reflective in the 0.864 micrometer band on ABI. Snow absorbs energy at 1.6 micrometers. Thus, snow, ice, and clouds made up of water droplets that look similar in the visible 0.86 micrometer imagery will look much different in the 1.6 micrometer imagery. This figure of a wave cyclone in the western Atlantic shows a cirrus shield that is much less bright than the lower clouds. That's because ice is absorbing a lot of the energy and it's not reflecting as much compared to water-based clouds. There's also a band of snow and ice on the ground over the mid-Atlantic states that shows up as dark. Now let's consider RGBs. To interpret RGBs, you must understand how colors are constructed in modern computer imagery. The color cube here shows the primary colors, red, green, and blue, at the 3 corners of the cube. White, all colors, and black, no colors, are at 2 corners, and the other 3 corners are color combinations. Yellow, red plus green with no blue, cyan, green plus blue with no red, and magenta, red plus blue with no green. All colors can be found in the color cube based on the 3 color combination. For example, orange is a lot of red plus some green, but no blue. Knowing how different colors are created will help your interpretation of RGB imagery. This slide shows how changing one of the 3 inputs will affect the RGB image. The columns show the red, green, and blue components and the derived RGB, which is kind of a true color. In the second line, the red component is only half as bright. The green and blue are still full intensity. In the third line, the green component is half as bright. And in the fourth, the blue component is half as bright. The RGBs from the 4 combinations are in the rightmost column. With less red, the RGB acquires a cyanish hue because blue plus green makes cyan. With less green, the RGB acquires a purple hue because red and blue make magenta. And with less blue, the RGB acquires a yellowish hue because red and green make yellow. You can create single-banded combinations of RGBs using an online tool at the URL on this screen. This web app includes current ABI data and allows you to choose single bands for the red, green, and blue components and create RGB combinations. In this way, you can explore the different possibilities combining single ABI channels. something to do when you're on a long airplane flight or if you're a passenger in a car. Here's a daytime image that combines the 10.3 micrometers in the red, the visible 0.6 micrometers in the green, and the 1.6 micrometers in the blue. Do you have a guess what you'll see? What color will the hurricane in the Pacific be, for example? Were your guesses correct? Water clouds are cyan, without a lot of red because they're warm, so there's not a lot of 10.3 micrometer information in them. High ice clouds, like over the hurricane, are yellow because they don't contain a lot of blue from the snow ice channel. Here's the same RGB as created in AWIPS. It's a bit different visually from what the web app created because the value bounds are a little bit different. RGBs that are present in AWIPS have changed at times in the past, but they are now in early 2025 relatively stable, and they're listed here. You can find additional information on RGBs at the link to a comment module on RGBs and at the link to UMetSat. There are 7 RGB images that you'll see next. Given the bands, maybe you can guess what you'll see and why you are seeing that color. But for some of the RGBs, that's far more difficult because a band difference is being used or only certain ranges of that band differences are included in the RGB. For the fire temperature RGB, 3.9 micrometer data are used for the red component, 2.24 micrometer is used for the green, and 1.6 micrometer is used for the blue. As the fire gets hotter and hotter, red data, which is almost always there, is augmented first by green, red plus green makes yellow, and then blue. So as a fire develops and increases in intensity, its color will change from red to yellow to white because as it gets hotter, it starts emitting more and more 2.2 and 1.6 micrometer radiation. The RGB uses only part of the dynamic range for each of the different bands, and a gamma of 2.5 is applied to the red component. If gamma is greater than 1, then the high end of the distribution is highlighted, so in this image the hottest pixels are emphasized. If gamma is less than 1, then the low end of the distribution is highlighted. In this case, for the red, the cooler pixels would be highlighted. That's not what you want for a fire temperature RGB. The gamma of 2.5 in the red here makes the fire region pop. The air mass RGB has a long history. It uses a split water vapor channel as its red component, the split ozone is green, and the upper level water vapor is blue. Channel differences used in this RGB and in others are viewable in AWIPS. For information on why the channel difference is part of the RGB, consult the quick guides for those channel differences. The orange regions in the air mass RGB, such as over Oklahoma and Arkansas, correlate very well with potential vorticity anomalies. Nighttime microphysics is another RGB with a long history of use. It uses a split window difference as its red component, the night fog brightness temperature difference as its green component, and the clean window 10.3 micrometers band 13 as its blue component. Many offices use this RGB to detect overnight fog, and that fog detection by the RGB arises from the night fog brightness temperature difference being the green part of this RGB. So those cyan features in Northwest Arkansas in the RGB, you note they show up also in the night fog brightness temperature difference. Day snow fog combines the veggie band at 0.86 micrometers, the snow ice channel at 1.6 micrometers, and the day fog brightness temperature difference, 3.9 minus 10.3. Because it includes 0.87, for which clouds are highly reflective, and 1.61, for which wavelength ice clouds are not highly reflective, this is one of several RGBs that allows a user to distinguish between cumuliform and cirriform clouds, and between cumulus clouds and snow. For this RGB, a gamma of 0.59 is applied to all bands, and that emphasizes the low end of all rangers. Dayland cloud is another daytime-only RGB using 1.6 micrometers in the red, 0.87 micrometers in the green, and 0.64 micrometers in the blue. This RGB has also been around for quite a long time. Note how the vegetation looks very green, water clouds are white, and cirrus clouds are cyan. SIM's natural true color simulates true color imagery from ABI. Even though a green visible channel is not present, it was one of the first simulated true color RGBs that were in AWIPS. GeoColor is now there as well. Both GeoColor and natural true color use reflectance information in the veggie band as a proxy for green. GeoColor is sharpened by removing atmospheric effects of Rayleigh scattering from the satellite signals. I've mentioned gamma a couple times with the RGBs. AWIPS includes gamma control to manipulate the look of RGBs under the composite option menu item in AWIPS. To access the control, right-click on the annotation label in the RGB image and then click on Composite Options. Gamma controls where most of the contrast exists in the RGB. For smaller values, the darker part of the grayscaled image from dark, warm to light, cold shows more contrast. And for larger values, the brighter part of the image shows more contrast. In addition to gamma, the min-max values for each input can also be adjusted. Here's the same image as the last slide, but with the gamma change from 0.6 to 0.2 for the green part. The warmer part of the green, the low-level water vapor, is emphasized now, and those features become more apparent and greener in the RGB. The 16 bands on ABI offer unprecedented geostationary observing capabilities. Each individual band can be used to observe phenomena, and band combinations or differences can highlight features or levels in the atmosphere. Furthermore, RGB imagery can further bring out information that is present in the component bands. A good practice when interpreting difference fields or RGBs is to have the component pieces at hand. Fields in one can be better interpreted if you have the ability to interrogate fields in the originals. Here are some internet resources to browse. This includes quantitative products that are available that nicely complement the channel differences or RGB products that are more qualitative. And in fact, you can load RGBs so that when you sample them, qualitative products show up in the sample probe. Quick guides on channels, channel differences, RGBs, and baseline products are also available at the links. This concludes the multi-channel interpretation part of the Satellite Foundational course for GOES-R. Thanks for listening.